program that we started or ended with, I think, in lab class or whenever we were talking about the viewports. Now I've just set this back into one viewport for the entire screen, and we just have some things moving around there. I think I'll take the red box and kind of see if we can move that around a bit. So first things first, and obviously I'm doing a lot of these just programming right into the main file, the lab1 game.java file. It's always nice to kind of split these things up, make a little class that actually holds, you know, the position and orientation and direction of some object, and another class, you know, split it up a little bit. But I'm just doing it this way to look at exactly what we need. So we have the red box, and now we're gonna float. So what we could do, which would be nicer really, would be to go in here, say which, this is lab 2, or we can do something like adding add a class, call it point3D.
Sorry, quick question.
Yes, please.
The code lock. What is lock?
It stands for location. And what these variables are, these, okay, I'm gonna do here public x, no, public float x, public float y. So these variables that end with lock, it stands for location. And what these variables are, they're simply identifiers or pointers to variables that we're using in our shader program. So for instance, position lock, it's the location of our position variable. And the position variable is really just a vertex, like the position of the point that we're rendering now, or that we're sending through the vertex shader now. Model matrix lock, it's the location of the variable that holds the model matrix, which is a transformation matrix. So if we go into our shader program, the shader is always written in the OpenGL shader language. And the OpenGL shader language is more or less C, except it has some special operations like matrix multiplications and something that are specifically designed to be compiled on hardware graphics cards. And this code will actually be compiled on your graphics card. It's not compiled along with the Java program. So the Java program is compiled. This is simply stored as a file, and in this file, the shader program is sent and just sent into your graphics hardware and compiled there. And so when it's compiled, it'll have these variables here. Here we have something that's matrix 4x4 matrix, and it's called uModel matrix. So that's a variable in our shader program that when we compile the Java program, this program will not have been compiled yet. So this happens in runtime, whatever. So this happens in runtime, and then we say, when this finally runs, we say now our graphics hardware has compiled this, and we make it do that here. So we compile these shaders on our graphics hardware. We make a program, create a program with both of the shaders that we've compiled, attach these shaders, link this program. So after this runs, actually, if we make errors in our shaders, we can't see them until we've run this code. So it's in runtime that we actually see those errors. So we have to make sure we have some lines that kind of spit out the errors for us so that we get the errors from the hardware compiler on our graphics hardware all the way up to our program. More on that later. But the idea is then, I say, inside the rendering program that I'm working with now, that I've now compiled, called u_model matrix. And that's the variable that is here inside this shader program. And I say, take this variable and give me a link to it so that I can stuff data into it whenever I want. And that link or that pointer is stored in this integer variable, which is the matrix location. So all the lock variables are just integers that hold a location to a variable in our shader program. So it's our link to sending stuff into our shader. So does that answer the question?
Yes.
Good. We'll talk more about this later when we actually talk about the shaders. But it's nice. Whenever these questions come up, please ask. We can talk about them a little, and then later on they'll make more sense when we actually start talking about that particular material. So now we have this point here, and I'll just make a vector as well. New class for 3D. In the end, we might, or in some of the other videos, I make classes point 3D and vector 3D, and then make actual operations on them, like addition and subtraction and cross product and dot product and stuff. So, all right, public float x, float y. And the reason I'm making two, even though they're exactly the same, is just so that our program will be better readable. We know what is a vector and what is a point, because we use them differently. In the end, we might add more things to this. Sorry? There will be a z, but right now we're doing this in 2D just to look at the time management thing. So let's keep it simple for now. Okay, so let's make it private point 3D. Position. So since we only have this one position now, we'll just call it position, and somewhere here in create. Like I said, please make your programs more tidy than I'm doing now. Position equals new point 3D. Position x equals just 100. And y as well. And then we actually want to say, all right, okay, go down here, and when we're rendering this red square, which is probably this one, now we want to do the translation to position x, right, and position dot y. All of these, we'll add 3 dimensions to all of these later on. Right now we have these very simple translation and scale operations. We're going to add to this so that we can do huge combined transformations in 3D. But for now, this is what we need. Okay, same program, except now we have draw scene here, we have display, we have update. So I like to keep update and display separated. Display has everything to do with OpenGL, taking our data, taking our vertices, taking our positions of everything, and sending it into the OpenGL pipeline. So setting our colors. So in here, I'm calling GL clear, and then I'm calling draw scene. I'm setting up the viewport. I'm doing everything that has to do with rendering things to the screen. But nothing in there should be actually changing any of these variables. So changing a position is always part of the update function. That's kind of where your game happens. Inside the update function, you should have your collisions, you should have your physics, you should have your gravity, you should have your thrusting motion. All of that should be inside your update function. So yeah, you can do it inside just touched. So now I'm going to say position.x, and you've already done stuff more complicated than this. Plus equals, right? And then we just put some number in here. So this is for each frame. I'm going to move this by 5. If I hit with the mouse. So what happens now is, okay, it's just touched. I'll put this on is touched. So while I hold the mouse, this is moving. And then it just moves off the screen. Okay, so this isn't about, you've already done this, and you've already made it stop at the edges, and you've made it bounce around. What this is about is the idea that if I, for instance, go into my render function, which now just calls update and display, if I go in here and do something like thread.sleep and have it sleep for 100 milliseconds each time. And I have to put this into a try catch. Boom. Okay, so every single frame that I render is going to take 100 milliseconds longer. So this is going that much slower, right? Now I'm going to sleep for 10 milliseconds. Sleep isn't that exact, so it's not going to be exactly 10 milliseconds, but it's faster now. And if I don't sleep at all, I wonder if I can just take this out and have an empty try catch, or if Java will tell me that that's.
Sleep for at least 10 milliseconds. If you do it like this.
Yeah, I know, but I'm not worried about how exact it is. I'm just kind of showing that, okay, now it's really smooth. We're just rendering each frame as fast as we can and then rendering the next. And it's always moving 5 pixels because now our window and our viewport are equal sizes. So moving at 5 is moving at 5 pixels. My question is, if I have a really slow computer and my computer works like this, as if it's sleeping for 100 milliseconds each time because it takes so long rendering. This computer game is a different game than the one on a faster computer. Everything goes faster. I don't know how old computers you've used, but I don't know if you've taken a game that was designed before CPUs and graphics hardware was so different that people needed to actually make sure that everything runs as fast on computers. Instead, you had a 386 computer, and someone who made a game for that computer knew exactly what it would run like because it would run on that same processor over every computer, and they just designed for that processor. And then you take that game and you install it on your brand new 486 computer, and you just couldn't play the games because everything happened so fast that you couldn't even see it. You'd lost the game in a millisecond because everything just went all over the place. Has anyone here experienced this when they switch computers? Okay, still some people who are old enough. Anyway, my question is now, how do we fix this? What can I do in order to make my game run the same on this ridiculously slow computer? Okay, nothing is going to be this slow. This is 10 frames per second. That's just not enough to be smooth. But let's imagine one is running 25 frames per second and another is running 100 frames per second. Both are good enough to play a computer game. One is simply smoother and better, but both are good enough to play the game. But I want the game to be the same. I need everything to be the same speed. So what can I do? Okay, check the time between the frames. I can't really check the time that the current frame is running, but I can check the time that it took the last frame to run. So if I have to make this from scratch, for instance, if I'm making my program in C++ and not in Java, there's probably something you can find to do this. But in the first programs that I did this in, I simply called like current time millis or something, whatever the operating system had to tell me what the current clock time was exactly now. And I called that each frame. And then the next frame, I'd call it again, and I'd simply have the last frame stored. I'd take the difference. And this was a number that I can now use to scale all of my movements with. So first thing is, in my update function, luckily, libgdx here has gdx.graphics. Delta time. Okay. So it's simple enough to use the system, to use Java or C++ or whatever, just to tell you the current time of the operating system. There are functions for that, and then take the difference. libgdx gives us a simpler way here. It has get delta time, and the nice thing about that is it gives us a float. That is the time of the last frame in seconds. So you don't have to do those calculations. Say, okay, I have it in milliseconds, or if I'm working on Linux, I can have it in microseconds. And then I have to take this and I have to flip it into seconds and change it into floats. So here we have a single function, and I can say float delta time equals this. So what do I do with delta time now? Okay, so delta time times 5. Okay, so this how far am I going to move now? How fast am I going to move? 5 pixels per second now. So I think that's a bit slow. So let's make it a little bit faster. Main thing is run it, and when I hit it, it should be okay, about 500 pixels per second. If I now go into my rendering function here and say I'm just going to sleep for 10 milliseconds, so I'm on a faster computer, still moving 500 pixels per second. More or less as fast. And now I take this entire thing out. And still moving same speed, just smoother. So it doesn't matter how fast the computer is. Of course, this won't be exactly the same. If you have a character that's moving and rotating at the same time, it's not exactly the same to do this in 10 steps as it is to do it in 100 steps. It won't be exactly the same, but if you're doing it in a single player game, the feeling will be more or less the same between computers. If you're within the range of a usable speed, 24 frames per second or more, then it should look more or less the same. So this is the basic idea behind this time management. This is all there is to it. The idea is when you run something on your computer and it looks nice and you hand it in as an assignment, it should look exactly the same when I run it on my computer. Whether I do it on my laptop, which is probably slower than your computer, or if I do it on my desktop back home, which I hope to get a proper graphics card in very, very soon, and will run your assignments really smoothly and really fast. But I don't want your assignments to run so fast that I can't see them. They need to run equally fast on both these computers, just smoother on one. So that's the idea. So now I'm basically taking this idea here and just applying it to this constant speed. So now I have this speed, constant speed here for the x, which is 500 per second. What if I want to say, I'm going to make another variable here, vector 3D, and call it speed. And that holds both the speed and direction that I'm going in. So I'm going to say speed equals new vector 3D, speed x equals 300, and speed y equals 80. There should be some kind of diagonal speed, and this needs the f for float. So what do I need to do here now in my update function? I don't want to just change x by a constant number per second. I want to change the position by the vector. So out of the mathematics that we've been doing, what is this? What do I have to set up here? I'm basically setting up a parametric form kind of for array, my traveling point. So we can do plus equals, but we can also do just, we say the new position x is position x, which would then be our point A, plus p, which is a parameter, that is how far are we moving within this frame, times c, which is our vector. So position is A, delta time is t, and speed, in this case, is c. And like the parametric form works, we can do it separately in x, y, and z dimensions. So we need to do this in 2 lines here. Or, of course, we could simply make a function on position or on point and vector, where I can say I can add a vector using a scalar to a point, and then I just have a single function where I throw the vector and the scalar in, and the function does the rest. Here I'm doing it in 2 lines. like so. So what is this going to look like? Okay, so it's moving along that vector that I set up. Now maybe we want to change this vector somehow. Like, what if I want the box to pull towards the mouse every time I click? I want it to have 0 speed to begin with. Or let's start with just changing the speed that way. Then we can start thinking about how we do it with acceleration. So how do I do this? If I still only want it to move when I'm touching, but when I'm touching, I want it to actually pull towards me. We can actually skip the speed here, add it again later. What do I need to make? I have the object somewhere, I click somewhere else. I want the object to move towards where I clicked. I don't want it to just go there, I want it to move there at an even speed. What do I need to do?
Find the vectors.
I need to find the vector, and what is the vector?
The point of the mouse minus the point of the box.
Yes. So we'll just make a new vector, or we can use the speed vector, we have it. Speed.x then equals tdx.input.get x. That would be the x coordinate of the mouse. So this works because we're working in a window and a viewport that are the same size. This will be a little bit more complicated if you change that, but this is simple enough now. Okay, this minus what? It's the box's current position. Position dot x. Okay, and we need to do the same with y. And we already know how we have to change y, right? This can't just be y, it needs to be dx dot, what was it again, graphics dot get height minus this, and let's just change it to float while we're at it. So, and this as well, let's make it float. Okay, anyway, so we're taking the x coordinates, subtracting the x coordinates of the box, we're taking the y coordinates, subtracting the y coordinates of the box, and then we'll just stick speed x and speed y.
You're using speed y x.
Yeah, thank you. If I did everything correctly, this should work now, right? Yes, that's the thing. See? It slows down as it comes closer. That might be what I want, because this might be a computer game where the distance from the mouse where I'm dragging has an effect on this. But yes, I should probably normalize it if I want it to happen at an even speed. So, do we add a normalize function into the vector and use that, or should we do it here? We can go into the vector and say public normalize. So what'll that do? Yes, void. Okay, what'll this look like? I need to find the length. So float length equals math dot. So I'm just going to do everything, nothing cheap and fast, just obvious math here. Square root of x times x plus y times y. Right, and then I should say x equals what? Sorry. So what is x equal? I found the length. What do I do with x? x divided by the length. Okay. And the same for y. Okay, so now I've normalized it. And then I can say, okay, now I have a way to have it a unit length vector. And then I might go into my game and say, well, fine, speed dot normalize. But then I have to say, okay, delta time speed, and then I have to do it times whatever speed I want to actually move at, which might be the speed 300. Or I might also say I'm going to have a special version of normalize on my vector. One is just normalize to unit length. The other is normalized to a specific length. Just new length. And then I'd say this would be new length times x. Okay, either way. So now we can do this all in one line and say I'm going to normalize it to 300. And then I have my speed. So this should be even speed, right? Please stop me if I'm going too fast or too slow or something. Okay, so now it's even speed. And I can just move it around while I hold it down and it'll follow my mouse. Even speed until it hits, and then it like vibrates there around it because it's always going, you know, it never hits exactly. Maybe, how could I make it stop vibrating and just stop nicely? Yeah, just give a buffer here. So then we can say, we can just say if speed dot x is greater than, no, that's not enough. Then we can go and we can go into vector 3D again. And we can make public float length. Say this simply returns this. Right? So we have a way to get the length. Say if speed dot length is greater than, let's say, no, 10 is too much. 4. Then we do this, otherwise we skip it. Fair enough. And then it should stop nicely. But again, this is just little fixes. And this is what you do in computer games. You want everything to work like perfectly and generically and you know, like almost real physics. But in the end, it's okay to just say, I have a little vibration here. I'm just going to put a little switch. I'm just going to put a little check and just make that not happen anymore. Or you can go into really complex math and make sure that everything is absolutely 100% realistic. I'm not as much for that kind of computer game as I am for just the, you know, Nintendo style cartoony computer game where you can just do whatever you want and it looks nice. Okay, so now we have this. What if I now want to say, I don't want it only to move when I'm holding down the button. I actually want it to move the entire time, but when I hold down the button, I want to give it a little pull in that direction. And when I let go of the button, I want it to continue in the direction that I gave it. What do I have to do with speed to begin with? Yeah, well, I don't even need an else statement. I can say this I'm always going to do. Okay, so I'm always going to do this. And if I even run it now, we'll see that it just goes, and then I hit here, and then it goes. Okay, so this is doing this. This is something, but this is not really what I asked for, is it? I can still do this, but when I let go, it continues. But I want to give it a nudge every time. When I hit it, I don't want it to just come to me. I want it to kind of slow down, and then I want to feel like I have the control of an elastic band. And every time I hit it, I kind of hit the brakes a little bit, and it bounces a little bit towards me. Do I need more vectors here, or do I need to use these vectors differently? So here, for instance, I'm just saying speed x equals this. Really what I want. Sorry? Yeah, it kind of has to add something to it. So let's say that I'm going to make a new vector here. Just vector acceleration. Sure. 3D was it supposed to be? 3D. Okay, and then I'm going to say, because I only want to, so I'm going to do something here to acceleration. Yeah. Okay, this I'm kind of taking out because it doesn't matter anymore. I don't want it to stop. I want it to go past me and bounce around. But every time, if I'm holding the button, I want to say speed.x. I add to that acceleration x. Okay. And the same with y. The question is this exactly what I want acceleration to be? Well, only when I'm holding the button down. So I'm setting acceleration to this length that I have. It's probably a bit too much. So we're gonna accelerate. I can't write this properly. Acceleration dot normalize, and we have this function where we can normalize to a specific length. But earlier it was speed per second. So it was how many pixels do I want it to move per second, and we said what, 300, and that was a nice speed. Now it's added pixels per second. So how many pixels of speed, or how much speed do I want to add per second? So acceleration of 300 is a bit much probably, because it'll very soon. Let's try 50. There's one more thing. Is there something missing here? So when I add acceleration to the speed, do I also need delta time? Like, what is acceleration in the math where you learned acceleration? Kilometers or meters per second per second. So it's divided with the seconds twice. Does that make a little sense that so obviously delta time is a fraction here. I'm multiplying the speed with time, and I'm also multiplying the acceleration with time into the speed. So when we finally change the position, we have it twice in it. Like acceleration is meters per second, whereas speed is meters per second, and position is just meters. All right, so we'll do delta time times acceleration. So the acceleration is only affected by how far away the mouse is, but the acceleration is added to the speed with an effect of how long the frame was. So more acceleration is added if the frame is longer on a slower computer, and then we add it to the position in the same way. And let's see what happens. Okay, not enough acceleration. And what I want to do is to start it off at 0, right? So speed starts off at 0. We saw it slow down a little bit, but probably not enough. I just didn't hit the mouse button. Okay, do we want more acceleration? I think so. Maybe 300 was fine, because we're kind of diminishing it with time so much. See what happens now. This might be too much. Why isn't it working backwards? Yeah. It might be that the program is a little bit off. Okay, it's working. Just giving it a little nudge. We just have to make sure that it doesn't go too fast, because then we lose it off the screen. So it's working. Come back. All right, there I lost it. Fair enough. So I don't know. Let's make it a little bit slower. That is the acceleration a little bit less. And see what happens if we make the frames a little bit slower. Here. Thread sleep again. Time's almost up, so. Okay, so this is the feel we have when we're doing it on a fairly slow computer. We can see that it's not as smooth as before, but it's fast enough to be usable as a computer game. Or is it just me? Maybe the projectors are so jittery anyway that you can't see that it's less smooth. To me, it feels a little bit less smooth now, but if we now take the sleep out and run it again, same numbers, it's the same feel to the game. The game feels like it has the same speed. And if I add this again and oops, make it a little bit more, like 60 or something. Okay, now it's definitely a lot slower. Sort of the same feel to the game. The game isn't happening slower, the computer is rendering slower, and so it's less smooth, but it's still the same speed. So that was the main idea with this lesson, was this idea of how can I make sure that everything I add, both speed and acceleration, is added based on how fast the computer is running. So a faster computer needs less changes per frame, a slower computer needs more changes per frame, so that the overall feeling is the same. But with that, I think once I put this online, you should have a little reference to kind of starting this motion thing in your second assignment. Next week, we'll talk about the assignment itself more, but definitely read the description of the assignment and start kind of thinking about what kind of game you'd like to implement. So class dismissed and have a nice weekend.